Hello everyone, I'm Binbin Tang from China. Here I want to talk about the secondary reconnection at the Earth-Frank magnetopause. Here is the co-authors of this study. I want to begin with the Danji circle, which is a framework of the Earth's magnetospherical plasma circulation. And we know that it's primarily driven by the day-side magnetopause reconnecting here and the night-side magnetopause. But this picture shows the 2D cartoons. In 3D, the reconnected open field lines at the day-side magnetopause and it can be dragged to the Frank region and present a large Bx component which can form a large magnetic shear locally due to the Bx. So it provides favorable conditions for local reconnection. Here we show an example from the MMS observations, and this event is observed in 2018 June 1st. The IMF is southward in Z and also has a negative By component. MMS crosses the magnetopause from the downside, which we can show that it's from magnetosphere to the magnetosphere, and the Bz component changes from negative to positive, and the plasma density decreases. And during crossings, MMS observes a northward ion jet, which is quite urbanic. This shows provides basic signatures of the primary magnetopause reconnection. In the primary reconnection, we can also find something different with the usual day-side magnetopause reconnection. For example, the Bx component inside the primary exhaust is positive, and the plasma flow is negative in x direction, though it's still much smaller than the solar wind speed. This is consistent with the dragging of the reconnected open field lines. And what we want to say that inside the reconnection, primary reconnecting exhaust were close to the magnetosphere boundary, as shown by this black line. We found an unexpected ion component, which flows mainly in the negative x direction. And together with the large Bx magnetic shear, so we want to think about there's a local reconnection. Here is a zoom-in of the time interval around the local magnetic shear, and we have changed the data into the local LMN coordinate system. We found that the primary ion outflow has changed into the shear flow for the possible secondary reconnection. You can see that it's positive in M direction and negative in L direction. And we can also find there are some variations of the magnetic field, two component ion distributions, and we will see that if we see that this can be well explained by the local secondary reconnection. if we take that MMS and goes a partial excursion into the secondary reconnecting exhaust, shown by this green region, which we can observe the ion signatures and the final four crossing near the X line, which we can study the electron behaviors. First off, we can look at the ion behaviors, which basically shows the two component, and here, for example, two component here and two component here. As we just say that we can compare the observations with the theory, which is a symmetry reconnection with a flow shear, predict the outflow plasma density and predict the drift of the X line due to the flow shear and the variation of the outflow plasma speed in the frame of the spacecraft. This is a predicted numbers of the from theory. We can find that in the observation, the outflow speed matches with predictions, and this shows the partial density of this secondary component, which agrees well with the theory. And also we found that as this 3-term interval is closer to the local X line, the ion speed decreases. So it shows that consistent with that MMS is closer and closer to the X line. And if we look at the time interval, the final four crossings, this shows the data from MMS1. We can find that there's a B minimum, which is less than 2 nanotesla, and we can find that the electron bulk outflow, meaning the L direction, which is much larger than the predict reconnecting outflow speed. We can also find the electron temperature and isotropy at the two sides of the BL reversal, which is due to the counter-streaming electrons. And around the BL reversal, we found the electron pitch angle mixing. So all this, again, is consistent with the reconnection picture. We can also compare the observation from the different MMS spacecraft. As we know, the X-time drift speed can be inferred from the theory, and the normal speed can be estimated from the timing. So basically, MMS crosses relative trajectory shown in this way. MN2 is the furthermost one to the X line. So the B minimum here from MS2 is not clear, but the whole pattern of the BM component can be seen from all four MMS spacecraft if we consider doing a finite guide field. We note an interesting part is that there are two JM current sheets. One is around the BL reversal, and the other one is close to the magnetospheric side. There are two things we should to note. First, the magnitude from MMS2 is the weakest compared to the other spacecraft, and the peak-to-peak separation is about 16 kilometers, with about meaning that 0.35 EI. Comparing with the particle in cell simulations, it suggests that MMS is not far from the X-line. Due to the small B minimum, which is favorable for the magnetic curvature scattering, and we can see that from MMs 1, 3, 4, we can get mixing, but MMs 2 is not that clear because it observes minimum at MM2 is not very small. We can also observe the geotropic electron distributions, namely the electron crescent, and it's an indicator of the EDR crossing, and together with the current, electron velocity, and other signatures shows that quick evolution of the connection at a scale of MMS operations, and is consistent with that MMS crosses the vicinities of the EDR. We also note that at the counter-streaming electron, also namely the recurring cybertrix, observed broadband high-frequency electrostatic waves, which provide additional evidence for local secondary connection. Finally, I want to show the auroral signatures observed by DMFP. The MMS footprint is marked by the circle here, is at one end of the bright auroral. Considering the similarity of the observed aurora with the north-south aurora streamer in the midnight ionosphere, which is closely related with BBF, we suggest that the aurora observed at the downside ionosphere is closely related with outflow of the secondary reconnection, so that the secondary reconnection can transfer solar wind directly to geospace. Here we show the local secondary reconnection at the flank magnetopause. But why this segmentation can happen? So it needs some preconditions. Based on observation, the primary reconnection outflow is northward, so that the open field lines should connect to the north hemisphere. However, the Bx, if we remember, inside the magnetosphere is negative, means that the MMS enters into the southern side of the tail current sheet. So considering the IMBY is negative, which will twist the magneto-tail current sheet. You see here, based on global MHD simulations, it will cause an offset of the tail current sheet to the equatorial plane, so that MMC here can observe a large Bx shear, which is favorable local reconnection. So here is a summary. We observe the local secondary reconnection at the flank magnetopause, which is basically a cross-scale coupling process. And as this reconnection reconnects the open field lines and the closed field lines, so that it's a neutral type reconnection. And we suggest that this reconnection provide the important modifications to the classic tangent circle. Okay, that's all. If you have questions or comments, please write to me.